Hi everyone, hi again. Now in this section we're going to learn about carbon hydrogen stretching vibrations that hydrogens are attached to different carbons. Okay, so now in this case you can see we are looking at the carbon hydrogen stretching frequency attached to a sp carbon triple bond. This carbon, remember we learn the hybridization when you have two electron groups attached to the central carbon, that is sp hybridization. Okay, that's going to be, this carbon is going to be sp hybridized. And then when the hydrogen is attached to carbon-carbon double bond, this carbon, so there are, it's not showing the other hydrogen or the other group on that carbon, but it's a double bond, so that is a sp2 carbon. And then this carbon right there is sp3 carbon. So we have hydrogens attached to sp carbon, sp2 carbon and sp3 carbon. And these carbon hydrogen will have different stretching frequencies. Now the first one, which attached to sp carbon, it stretches around 3300, and then the sp2 is about 3100 to 3020, and then sp3 carbon and the hydrogen stretches 2960 to 2850. So which one do you think is a strong bond? It is the sp carbon and the hydrogen, the first one. Why is that? Why that is a strong bond? Remember, so we can look at what is the S character, how much S character in each carbon. Now in sp carbon, what is the percentage of S? It has 50-50, right? 50-50, because one of the S, one of the P, so there is a 50% S character in the first carbon. What about sp2 carbon? What is the percentage of S? That's going to be, you take 1 plus 2, 3, and 100 divided by 3. So that's about 33% of the S character in sp2 carbon. How about in sp3? That is about 25% of the S character. So the more S character an atom has, that's going to be more withdrawing electron towards it, making it a more stronger bond. Remember, the S orbital look like spherical in shape, whereas the p orbital look like a dumbbell. So in which orbital do you think the electrons are more closer to the nucleus? It is the s orbital, because the shape of the p orbital is going a little bit away from the nucleus. So the more s character an atom has, the electrons are more held close towards the nucleus, and as a result you can have a stronger bond. So carbon hydrogen will make it a strong bond, then the sp2 carbon, alkene carbon and the hydrogen, and then the alkane carbon and the hydrogen. So as a result you will see this pattern in the wave numbers. 3300 sp carbon and the hydrogen would need more energy to vibrate those molecules, or the stretching vibration. As a result, have a higher frequency and a higher wave number. Okay. Now the aldehyde, this is an aldehyde, and also this carbon is, what is the hybridization of that carbon? How many electron groups are there? Remember, the electron groups are going to be single bond, double bond, triple bond, or a lone pair. They are considered as electron groups. So this one has 1, 2, 3 electron groups. So when you have 3 electron groups, what is the hybridization? That's going to be sp2. So this carbon right there is also sp2. So hydrogen is connected to a carbon which is sp2. So that stretches around 2820 to 2720. Okay. The strength of a carbon-hydrogen bond depends on the hybridization of the carbon. So you can see here, this is methyl cyclohexane. These three hydrogens we are looking at, or the other hydrogens also. Hydrogens are connected to a carbon which is sp3. All of these carbons, in fact, are sp3. Okay, so they stretch a frequency less than 3000. sp3 carbon hydrogen stretching frequency. And this is carbon hydrogen. This is a probably this is a bending. Okay, sp3 carbon hydrogen bond is the weakest, so its stretch occurs at the shortest wave number less than 3000. We are looking at this 3000, so right less than 3000 is going to be sp3 carbon hydrogen bond stretching. And then we can compare it with a sp2 carbon hydrogen stretching. Now this one is cyclohexene. So the hydrogens you have here and hydrogens you have there. Let me draw that for you. So there is a hydrogen here and there is a hydrogen here, and then you have hydrogens in all these places. So this hydrogen is attached to a sp2 carbon. This also attached to sp2 carbon. So you can see there is a little band right there. That is due to the sp2 carbon and hydrogen stretch. And then this over here is due to these carbon hydrogen, because that is sp3 carbon hydrogen stretch. Stretching vibrations require more energy than bending vibrations. So these, yes, I was correct. So these are the bending vibrations, these ones that we saw in the other one also. See, these are the bending vibrations. Okay, bending vibrations. Okay. sp3 carbon hydrogen stretch occurs at less than 3000. You see, these are less than 3000 sp3 carbon hydrogen. sp2 carbon hydrogen stretch occurs over 3000. So this molecule has sp3 carbon hydrogen stretching as well as sp2 carbon hydrogen stretching. So you can see this little peak over there. But in our previous one, do you see there is nothing over here, because there is no sp2 carbon hydrogen. Okay. And this shows where the carbon hydrogen bonds bend. For the bending vibrations, it doesn't need that much of energy compared to the stretching. Stretching involves more energy. That's why we saw stretching somewhere here. And in fact, this is benzene. You can see these, all of these are sp2 carbons. And then the hydrogens attached to that would appear above or greater than 3000 area. Over here, that's going to be the hydrogens on the benzene ring, carbon hydrogen stretching. Whereas these ones, this hydrogen and carbon and these hydrogens and carbons, they are bonded to sp3 carbon. So that's going to be these ones. Okay. If I draw these hydrogens, these red hydrogens, that's going to be these peak right there. And then these hydrogens, they are attached to a sp3 carbon. There could be these peaks below 3000 carbon hydrogen stretching frequencies. And these ones over here, they are going to be bending vibrations. sp3 carbon hydrogen bend of a methyl occurs at less than 1400. Less than 1400, that's that. sp3 carbon, that's a bend. And these are stretching. Okay, remember we learned that there are two types. They can either stretch or bend during their vibration. And then the sp2 carbon hydrogen bend of a methyl and or a methylene occurs at greater than 1400. Okay, I got it wrong. Alright, So let me correct that. Okay, so this one. Okay, that is, so this one is the less than, it's okay. 1400, that's this one, sp3. sp3 carbon hydrogen band of a methyl occurs at less than 1400. You see, this is the 1400, less than 1400. That's methyl bending. And then the sp2 carbon hydrogen band of a methyl or methylene occurs at greater than 1400. That is going to be these peaks. That is coming from benzene ring. Okay. Okay. So these are some values for the carbon hydrogen bending vibrations. Again, you don't have to memorize any of these, but you can see the hydrogens depending on whether it is a terminal alkene, monosubstituted or disubstituted, and then the trans or the cis and tri-substituted, they have different wave numbers. Always we can refer to a table if you need to identify these bending vibrations. And one important thing that we need to have if you want to see a peak in the IR spectrum is that the bond has to be polar and there has to be a dipole moment. So that is when we can observe a peak. Okay. And if you don't have a dipole moment or you don't have any bond polarity, so then those vibrations will become infrared inactive. Now let's look at 1-butene. So we are looking at this carbon-carbon vibration, stretching, okay? So is this carbon-carbon alkene symmetrical alkene? No, it's not symmetrical, right? Because this carbon has a ethyl and hydrogen, this carbon has hydrogen and hydrogen. So there is a difference in bond polarity in this bond. Asymmetrical about carbon-carbon bond, and it has a dipole moment as a result. Now let's look at this one, 2,3-dimethyl-2-butene. We are looking at the vibration of this double bond. It's a symmetrical about the carbon-carbon bond, and due to that, this side and this side has the same bond polarity, molecular polarity. So there is no dipole moment. When the bond is being vibrated, the dipole moment has to change. To do that, we need to have polar bonds, at least not necessarily a polar, but at least a difference in bond polarities. But here it's a symmetrical alkene, so this would become infrared inactive. And then this molecule, it is pretty much similar, but now instead of methyl group, you have a butyl group on this end. So do you think this would be infrared active? Yes, it is, because there's no symmetry in the molecule. There is a difference in the polarity. It has a dipole moment, so this would be infrared active. A bond absorbs IR radiation only if its dipole moment changes when it vibrates. Okay. Now, what about carbon dioxide? Do you think carbon dioxide will give us a IR spectrum? So if you draw the carbon dioxide Lewis structure, it is like this. I put okay, so I put too many lone electrons. So that's one oxygen, and then so this is carbon dioxide molecule. Do we have polar bond in carbon dioxide? Is carbon oxygen bond polar? Yes, oxygen is more polar, carbon is less polar. Oxygen electronegativity is 3.5 and carbon 2.5. The difference is 1. So we have polar bonds. That's a polar bond. So that's oxygen is more electronegative. And this oxygen carbon also has a polar bond. Now, do we have a dipole moment in this molecule though? No, because the bond polarities get cancelled. Even though it has polar bonds, due to the symmetry of the molecule is linear in shape. Carbon is sp hybridized, linear, 2 atoms, 2 electron groups, right? So bond polarities get cancelled. So as a result, carbon dioxide will not give us a IR spectrum because the bond dipoles will not change as it vibrates. Okay. How do we interpret an IR spectrum? Now let's see, you are given this spectrum and we want to identify what are the peaks in it. The IR spectrum of 2-methyl-1-pentene. So you can see here we have a double bond. We have single bonds, we have carbon-carbon single bonds, carbon-carbon double bonds, we have carbon-hydrogen single bonds, and then we have carbon-hydrogen bonds attached to sp2 carbons, we have carbon-hydrogen bonds attached to sp3 carbons, all kinds of carbon hydrogens we have here. So what can we identify predominantly? We can see, you see here right below 3000 we have some peaks. And what are those? Those are sp3 carbon hydrogens right below that. Those are going to be these carbon and hydrogen, these hydrogen and carbon, this one. They all are sp3 carbon hydrogen. That's what appear here. And then we do have 2 hydrogens on this carbon, but that is a sp2 carbon. So that's why you see this peak above 3000, which is sp2 carbon hydrogen. And then if you refer to the table, you will also see that 1650 is this peak, and 890 this peak and this peak. If you look at the values, it will tell you those represent terminal alkene with 2 substituents. I would not expect you to figure that out. Okay. And then absence of bands, and then 1500 to 1430, 1500 to 1430, that is this peak, and 720, that is this peak, fewer than 4 adjacent CH2 groups. We have 2 CH2 groups again. So these last two, if you don't figure that out, that's okay. But if you can see this sp2 carbon hydrogen, sp3 carbon hydrogen stretching, wonderful. Okay. IR spectrum of 2-propyne-1-ol. Propyne means triple bond, and it also has an alcohol group. So you can see this broad peak. Whenever you see a broad peak, it should ring in your head. That's an alcohol right there. So around 3300 we have an alcohol group. And then 2950. Remember the 3000 area over here? Less than 3000? That is sp3 carbon hydrogen. That's this CH2 right there. And then I would expect somewhere here this carbon hydrogen stretching. Remember that comes little over 3000. Probably it may have overlap with this OH group. That's why we don't see it. And then the alkyne is the carbon-carbon triple bond, 2100. That's 2100 right there. That's the carbon-carbon triple bond, that one right there. Okay. And sp3 carbon hydrogens, that, and your alcohol is this alkyne. I just showed it to you. And then here's another one, IR spectrum of ethyl benzyl ketone. Now this one we have a ketone, and remember ketone comes somewhere around 1720. So this one, this huge peak, this is exciting peak. We're so happy when a carbonyl group shows up like a sharp peak like that. We know that the carbonyl is there. So that is your ketone carbonyl group, this group right there. Okay, and then you can see we have sp3 carbon hydrogen stretching as well as sp2 carbon hydrogen. So these are sp2 carbon hydrogens. Remember, benzene ring has hydrogen, though it's not written, and these are sp3 carbon hydrogen, like that. So sp2 carbon hydrogen occurs below 3000, sorry, sp2 carbon hydrogen occurs greater than 3000, sp3 carbon hydrogen stretching occurs less than 3000. So what are those peaks? So these carbon hydrogens, carbon hydrogens, they occur here, and these hydrogen, those are the sp2 carbon hydrogens, which is this sp2 carbon hydrogens. That's these ones are these peaks. Okay, and then benzene ring rises around 1600 to 1500. 1600 to 1500, these peaks, that's going to be benzene ring. And then the ketone carbonyl group is this peak right there, and then the methyl group 1380. Somewhere here. Okay. Now, in a spectrum like that, if you can identify these peaks as sp3 carbon hydrogen stretching and these peaks as sp2 carbon hydrogen stretching, and then the ketone carbonyl group, that would be wonderful. Okay, that's what we are normally looking at, but you can go into detail and figure out what all of these little peaks. Again, remember 600 to 1400 is the fingerprint. Functional groups appear 1400 to 4000. Yay, we're done with the IR spectrum, but it's very useful and a lot of information, and you learn a lot of chemistry, by looking at these spectrums also. Okay, that's really good. Okay, then I will stop here.